We can start by a ritual song and dance.
All right. Hello and welcome to this evening's lecture, Asteroid Impact, with Dr. Elena Adams. I'm Kevin Lewis, a faculty member in the Earth and Planetary Sciences department here at Hopkins. And today I'm your MC for this hybrid Hopkins at Home virtual and live studio audience event. So I'll start off, if you go to the web, and you can just go to the web and look this up, and look at the list of near-Earth objects that NASA tracks every day and night, what you'll find is that the Earth experiences close calls with asteroids every day, sometimes 3 to 5 times a day, and I show my undergraduate class this every year, what came close to the Earth. Today's object was a 50-meter object that passed about 20 times the distance to the moon. Not too bad. A couple weeks ago, we had one that passed less than 10% the distance to the moon. Close call. That was only a couple meters, probably wouldn't be too bad. But we know the Earth's history has been full of impacts over geologic time, and those include the exceedingly rare, right, extinction-level events that would obviously be very bad. So some folks may not know that Hopkins has a whole other campus down in Laurel, Maryland, the Applied Physics Lab, where all sorts of exciting spacecraft are built and sent all over the solar system. Today we're going to hear about how the Johns Hopkins Applied Physics Lab is tackling the problem of defending our planet from potential future asteroid threats. Shortly we'll hear from Dr. Elena Adams about the upcoming DART mission that's scheduled to happen in, well, it's already happening, but it's scheduled to impact in 11 days. And following her talk, I'll moderate a discussion with questions both from folks online and here in the room. And now let me spend a minute here just introducing our speaker. So Dr. Elena Adams has degrees in applied math, space science, space systems engineering, both the science and the engineering sides. She's now a program manager at the Applied Physics Lab, and she's worked on missions to the sun, the Earth, asteroids.
And not just throwing samples back to Earth, not just.
Asteroids, the Jupiter system.
That's right.
The Saturn system.
Yes.
And I know you've at least co-authored studies to other bodies in the solar system as well.
There happen. It's true.
She's worked to develop, she's led the development of new technologies to sample these objects in our solar system. And she's, among other things, the lead mission systems engineer for the DART mission, which I think means we'll have her to thank for successfully destroying the mission that she successfully led the design, build, and launch of.
Yes, looking forward to that in just a few days.
So
really
right now,
looking forward to it.
Yeah. So right now, DART is only 11 days out from its flight that's been going on for the last 10 months. The arrow is about to hit the target. It's this close, and it's traveling 15,000 miles per hour. So what I mean to say is that we should all be very thankful that Elena Adams is taking the time out of her very busy schedule, I'm sure, to come talk to us tonight.
Yeah, thank you. Thank you for that. That was an awesome introduction. I love talking about DART. Yes, definitely. Great introduction by our moderator. So I love talking about DART's my favorite mission by far. I hope that by the time I finish, you guys will be just as excited about it as I am. And I'm telling you right now, the next 11 days are going to be both terrifying and exciting at the same time. So I'll start in the beginning, which is to say that Earth, the space looks pretty dark around it, but it's actually surrounded by lots of debris that was left over from the formation of the solar system. And all of that stuff constantly is coming into the atmosphere. Some of it is really small, and we see a bright little flash, and we're all excited and make a wish. Other things are not as nice. So the government has been tracking that for a long period of time. So this is a map that shows the fireballs reported by the government, and there are multiple assets that do that too. So all those little dots are all different asteroid impacts that are going into the atmosphere, and some of them are bigger than others. The one that's really bright red happened in 2013. That was the Chelyabinsk asteroid. There was a meteor that went into the atmosphere. It was about 25 meters in size. 25 doesn't seem that big, right? You just said 50 meters. Oh, I'll tell you what happens with a 50-meter one. But so 25 meters, not that big. It actually, what detonated in the atmosphere, created a giant flash. People were driving around, that had their dash cams on. They actually took pictures of this asteroid. And as it came into the atmosphere, 90 seconds later, people heard a giant boom. A bunch of windows were broken. Over 1,000 people injured. It was the blast was 30 times the Hiroshima bomb. It was an amazing blast. But that's a 25-meter asteroid. So what happens? So I'll tell you a little bit about all the different asteroids and different sizes. What does that do to you? Okay. Let's start with the 4-meter asteroids. So 4-meter asteroids, once per year, there's a little asteroid that's coming in that creates meteorites. Everybody's excited. You get your own space rock. People, I think there was like one death recently due to somebody getting hit by a meteorite. But usually, it's just no ground effects. There's a bright flash in the atmosphere. And we think there's about 500 million of those asteroids that are in near Earth system. And so most of the asteroids we're talking here are near Earth. So as you know, there's a main belt of asteroids, and those are far away. Those are between Mars and Jupiter. 3AU, we don't have to worry about those so much. They're nicely kept in there. Then there's a bunch of asteroids that are actually closer to us in our solar system that are near Earth asteroids. And what makes them near Earth asteroids is that their orbits sometimes cross that of Earth. And if they get too close, this is when the excitement happens. So I'm not a big fan of that much excitement. Okay, let's talk about the 25-meter ones. This is the one like what the Chelyabinsk was in 2013. So that's once per 100 years, right? And those are airbursts, explosions, could cause widespread injuries if it happens over a populated area. And we think about there's 5 million of those around. Now, let's talk about the next one. Of course, the dinosaur you have to bring up the dinosaurs whenever you talk about asteroids because they're not here, we are. And the reason for that is many years ago, about 65 million years ago, there was a 10-kilometer asteroid that hit Earth. And goodbye dinosaurs, welcome humans, yay, but let's not be dinosaurs. Point is that, that happens not very often, once 100 to 200 million years. Let's hope that's not happening in our lifetime. And global devastation, mass extinction, etc. Okay, so let's talk about the 1-kilometer ones. What do they do? Those happen about 500,000 years. And those are actually creating about a 10-kilometer crater. And possible collapse of civilization, and I do like it when we put possible collapse of civilization on a slide. Always makes everybody feel very good. So the last one, but not least, are the ones that happen every 25,000 years. And they're about 160 meters in size. And those are the ones that if one like that comes in, you create a regional scale effect. That means that you basically create a crater that's 1 to 2 kilometers in diameter, and they're deadly over a metro area. So I'll show you what that means in a second. But The last row of this slide, you can see is that, well, how many of them we know where they are? So the 4-meter ones, we know pretty much nothing about because they're tiny, they mostly burn up in the atmosphere, they're very hard to track. All of these asteroids are incredibly hard to track. They're very dark, they're kind of reddish, so best to look at them in infrared, but we're sitting on the ground, we have our ground assets that are looking for these asteroids. And we know where they are, about 0.1% of the 4-meter ones, but we don't care, burn up in the atmosphere. We know a little bit more about the 25-meter ones, but also those are not as scary as the ones that are in the 10-kilometer range, where we know 100%. There's 4 of them. There's 4 of them. We know where they are. Everybody can sleep better at night. The 1-kilometer one, also possible collapse. I do love saying possible collapse of civilization in my talks. Those, we know about 95% of them, and we're doing our best to track them. It's about 900 of them in the population. But the ones we don't know about are the 42%ers. We only know about 42% of these 160-meter ones, the ones that would take out a metro area if one was to come down. Okay, so what does that do? All right, so this is the Barringer crater, and I hope that some of you will get out to Arizona. How many of you from here, from Arizona? Raise your hand. Anybody, please, come on. I know you like Nebraska, but oh, there you go. So have you been to the Barringer crater? Oh, well, this is just a disappointment here. All right, so there's a Barringer crater, meteor crater in Arizona. It's actually a funny story. A guy named Barringer bought the crater looking for an asteroid. And the asteroid came in. It was about 50,000 years ago, 50 meter. Oh, wait, you mentioned the 50 meter. But he thought it's a metallic asteroid, right? So it came in, and the guy thought, oh, this would be great. I'm going to dig in this crater, and I'm going to find all this platinum. And he spent 25 years of his life, I think, searching for that, digging through the whole crater, looking for the asteroid. Well, sadly for him, apparently when the metallic rock hits the ground, it vaporizes. So he could never find his perfect metallic asteroid. However, his family still owns the crater and charges huge amounts of money for you to actually go in and visit it. So please support Arizona economy. Okay. But here we have the crater that's 1.2 kilometers in diameter, 180 meters deep, that it created this 50-meter asteroid. And the thing with that one, is, in particular, I think it's so cool, is that it created a fireball out to about 10 kilometers. And then at 24 kilometers, you basically killed all of the animals and wounded them, and then created hurricane force winds to 40 kilometers. Okay, so I don't know. I used to think in kilometers a lot. Now I think in miles. So to make it more real, I'm going to show what happens to DC area when that happens, right? So here we are, overlay the 50-meter asteroid crater on top of it. So, so we're looking at DC, basically large animals, we're large animals, completely wiped out in DC, then hurricane force winds as far as Annapolis. So, thank goodness for NASA. So we have a program called Planetary Defense Program. There's actually a NASA office called Planetary Defense Coordination Office, and they were established in 2016. Their job, which they chose to accept, is to look for asteroids, track them, characterize them, figure out what to do with them, and then try to mitigate the threat. So DART is the first mission for this Planetary Defense Coordination Office, is to actually say, how are we going to mitigate the threat of asteroids? And there are many different ways to do it, and I can talk about them until the cows come home. One of them, number one, is the kinetic impact. By kinetic impact means you go and you slam into an asteroid. That's all you're doing. Very straightforward. Here you are. Here's the spacecraft called DART. And that's what we're going to be doing in 11 days. We're going to impact an asteroid. Of course, there are lots of caveats to how easy is it to do this. You are 105 million miles away. There are many different things that are going on. So I'll tell you about our challenges too. But at the end of the day, the planetary defense technique that we're demonstrating is called kinetic impact, and it's going to slam into the asteroid. The theory is pretty straightforward. If an asteroid is coming towards you, you need to just change its trajectory just a little bit, just enough for it to miss Earth. And that's what DART's doing. Except for this is a test. And we wanted it to be an extremely safe test. Even though Didymos, which is the system we're going to, is a so-called a potentially hazardous object, which means that it actually crosses the Earth's trajectory pretty close to Earth. We're making this a super safe test, and that's because we're going to a binary system. So let me show you a little bit about that. Okay, so in the middle, there's Didymos. We're going to the Didymos system. The asteroid itself is 780 meters big. So it's a pretty big asteroid. If that was going towards Earth, I would move to Mars. Then it has a little moon called Dimorphos that orbits around it. And the whole point of the DART impact is that we go and we hit the moon. So right now, the orbit of the smaller asteroid around the larger asteroid is 11 hours and 55 minutes. And after we hit it, we're going to change the orbit enough that it's going to be 11 hours and 45 minutes. And that's something that could be measurable from Earth. And in fact, it will be measured from Earth. On Earth, we have a lot of ground stations, a lot of telescopes, as well as some missions that are going to be looking at Didymos system after we hit it. And so what they're going to be seeing is that you're basically looking at the light curves. What are the light curves? Is as the moon passes in front of the larger asteroid, you're seeing the the brightness of the bigger asteroid decrease and then increase once it stops passing it. So you can see that you can also get a dip when it passes in the back of the asteroid, but these are technicalities. Point is that you can measure it from the ground, and you can do it from all over the place. So we actually have a worldwide campaign. You know, planetary defense, it's a global sport, right? We all are in it together. You don't know until really late in the game that if an asteroid's coming towards you, you don't know where on Earth it's actually going to hit, because the uncertainty on the trajectory of an asteroid is such that you can't really predict it until really late, unless you do a lot of observations, which is what people are trying to do, right? So we have our friends all over the world that have time on different telescopes, including on the James Webb Telescope, on Hubble, and even on a different mission called Lucy, which also has an APL built instrument. This is my advertisement for APL. That's going to be looking at the time of the impact to the Didymos system, and in hopes to see us actually impact. But what are we going to learn from this, right? Because, I mean, other than the fact that as an engineer, I love the idea of getting paid for, smashing millions of dollars worth of spacecraft. I mean, that's pretty cool. But you do have to learn something from this. Well, number one is that we do a lot of tests on Earth, right? Where we basically have some sand and a pellet, and then we hit the pellet with the sand, hit the sand with a pellet, and maybe the other way around, and then you see what kind of ejecta you create, right? You do that also with meteorites too. You don't really know, are the asteroids metallic? Is it a metallic core? Or is it all pieces of regolith that is all smushed together in a loose formation? So depending on what the asteroid is made out of, you will create a large plume when you actually impact it, or it will be small. It all depends on the porosity of the actual asteroid and how well congealed it is, how solid is that core. So you actually, if you create a really large plume, it almost acts like a thruster on the asteroid, and it will change the momentum even more. It will push the asteroid even more. So these are the things that we can't really tell from the ground, that you really need a space-based test to do this. And the reason for that, why would you really care about this? Is because if there was an asteroid coming towards Earth and you wanted to go move it, you need to be able to know how much you're going to move it, right? Because the last thing you want to do is make it worse. Or it doesn't come back in this year, but you didn't produce enough momentum that it comes back 2 years from now, right? These are the things when you're dealing with celestial bodies and their movement around the sun. There are many things that affect it, right? Gravity affects it, the solar wind affects it. Solar wind is all the particles that are coming out of the sun. So these are the things we care about. So characterizing this beta, really just how much you actually moved it, is extremely important. And as I said, we're not alone in this. This mission originally started as an international mission. It had a component from the European Space Agency and from NASA. So we are the NASA component. Yay, let's go slam into something. They're more like, oh, we'll go analyze things afterwards. So we have a sister mission called Hera. It's going to get there in 2024. And it's actually going to look and see what did we do. It has a couple of CubeSats. Oh, yeah, I'll mention our CubeSat in just a minute, too. Point is, Hera is going to arrive there in 2026. It's going to see what did we do, and it's going to measure the crater that we created, which we think is about 10 to 20 meters big out of a 160-meter asteroid. So just to give you a scale of things. And the DART spacecraft I'm just realizing that I didn't actually put any pictures of the spacecraft in there. I know, good moment, what can I say? But the DART spacecraft, I'll just start here. The DART spacecraft is actually here in the fairing, in the launch vehicle fairing on the right. And it's about 2 by 2 by 2 meters. It's a cube, very classy. And it has a next-see ion thruster on top and the Draco imager on the bottom. And you can see my friend Alexei standing next to the fairing as they were actually closing it up. So we launched in November this year. We like to make sure that everybody works through all their major holidays. So this was like right at Thanksgiving. So I'll just show you the video of our launch, which is always really exciting to watch. We in the Mission Operations Center are excited. Oh, there goes.
Falcon 9 and DART on NASA's first planetary defense test to intentionally crash into an asteroid.
Yep, and they said intentionally and crash, all in the actual broadcast. Usually they try to avoid these words. But
the job of Falcon 9 was to get
the cool thing about Falcon 9 is that they actually take a picture of you as you leave the launch vehicle. So the rocket lifts you up, and then at some point it falls off, and the spacecraft goes off by itself to do its thing.
We're in range
so you will see our spacecraft actually leaving the rocket. There it goes. We actually knew that it happened. It was good. I don't know. We didn't get to see it.
Of the DART spacecraft on its way, heading on its way to the Didymos system.
What a spectacular view.
Yeah, I agree with her. That was a pretty spectacular view. Well, so us in the Mission Operations Center, who actually had another 6 hours worth of work to do afterwards, we didn't see this amazing shot until about, I would say probably until the next day when we were all bleary-eyed and somebody forwarded it to me. I'm like, wow, that happened? That's cool. What? That's us? That's amazing. But yeah. So we're going there at an ideal time. So why do we want to go there right when it gets closest to Earth? So we launched in November 23rd, 2021. So we've been in cruise for about 9 months. And we are getting close to impact, which is on September 26th, 7:14 p.m. And I will have more advertisements later. So the reason why we're very excited about it is that the Earth, we're getting closest to Earth. And you can see that the Didymos system is actually following it in. We're following in the Didymos system. So we're going to impact when it's really closest to Earth. So you can actually use the telescopes on the ground to observe it and observe the change that we made, because that's an incredibly important part. Okay, so we've been using our imager the whole time. Our imager is called Draco. That is the eyes of our instrument. That is what we're actually going to be using to glide ourselves into the asteroid as well. And not only do we get to take really cool pictures of Jupiter, and by the way, if you go back and you look at Galileo's pictures of Jupiter, you know, images that Galileo actually had through his first telescope, these are about the same resolution, so it's a little embarrassing. But what are you going to do? However, we don't use it for fun. We're not taking those images of Jupiter for fun. We actually train our SmartNav, which is our autonomous navigation software. Oh yeah, wait, our spacecraft is autonomous. That's a thing too. So it's completely autonomous, and we train our spacecraft navigation using Jupiter. So what we do is we're actually watching Jupiter, and then we're watching the moons emerge from behind Jupiter. What you're seeing here is smart nav algorithms at work, where we're actually pretending like Jupiter is Didymos, the bigger asteroid, and then we're tracking Dimorphos, which is Europa. Actually, the few times the test didn't work, so I told the Europa Clipper people, like, Europa doesn't exist. I'm sorry, we proved it here. Not true, we just didn't see it. So yeah, it's been really great because we can track the actual Jupiter system, and you will see that it will, at some point, it will start tracking again. And then when it comes in, we lock on both. So we're actually tracking and locking on both. And that way, we make sure that our algorithms are all correct. And the good thing is that we also know that Didymos exists because we've been able to see it. And that was a big moment for us, too, because you go 107 million miles and it's not there. That would be bad. But no, it's here. We can actually see it, this little dot right here. This is actually an addition of about 230 images. It was taken in July. At this point, we're co-adding only about 100 images. But the thing is, we really know very little about the object we're about to hit. So this is what we know about Didymos itself. And it is very cool. In 2003, it came close to Earth. We were able to figure out its shape pretty well using radar. But when we look from the ground, what you're seeing in this image is tracking of Didymos. So it's just going across. There it is. There's Didymos. And every now the light dims. That's how we know it's a binary. So yeah, lots of faith on what we're going to do. But we know nothing about Dimorphos. We can speculate that it's made out of the same stuff as Didymos. We think it's about 160 meters big, but what shape is it, right? Asteroids come in all sorts of shapes and colors. They come in dog bone shapes, which are much harder to hit than one thinks, because when you're viewing it with a visible camera, what you're seeing is two blobs coming towards you, and you're like, where am I hitting? Am I hitting one or the other? What am I doing? So we don't really know what it's going to look like, and we're not really going to know until pretty late in the game. So this is our timeline to impact. You are here, which is, this room right here, but also you're 11 days from impact. We're starting to have continuous coverage with our antennas, where we do last maneuvers and doing a lot of different loads of parameters and lots of spacecraft stuff. Point is, we have a moment in time, which is at 4 hours prior to impact, where the spacecraft becomes completely autonomous. Before then, we're in a mission operations center. We send commands, we get data down, we make the spacecraft perform maneuvers, do tests, all by us doing things on the ground. So at 4 hours, the spacecraft becomes completely autonomous. At that point, you cannot see Dimorphos at all. In fact, you don't see Dimorphos, which is our target, until about 70 minutes to 55 minutes, and some models say even 35 minutes before impact. And at that point, it's just one pixel in the field of view of our camera, right? One little pixel. And the spacecraft has to figure out, oh, I've been tracking Didymos this whole time. Oh, that little speck that I saw, yeah, that's Dimorphos. I should stop going towards Didymos. I should start going towards Dimorphos. And that's what we do. It autonomously figures out where that asteroid is, and then it actually maneuvers itself all the way out to meet Dimorphos. And I had to stop because we used to call it A and B, and because, engineers. So we'll call it Didymoon, right? So we're hitting Didymoon. So it is actually kind of amazing, because at 2.5 minutes prior to impact, we stop maneuvering. And in the last 2 minutes, we really are just going to glide ourselves in. This is a quote from one of my favorite folks on the program, Mark Jensenius. He's actually a smart nav engineer who says that if you look on the map and you stop maneuvering over Indy 500, and then you glide yourself all the way into the Camden Yards, and you have to hit it. So in the last couple of seconds, you're actually going to get the best images yet. Oh, did I mention that we're actually streaming video back to Earth the whole entire time, the last 4 hours? So we're streaming video, and we're going to know because the asteroid's going to get bigger and bigger in our field of view, and then the signal is going to be lost. We're moving at 14,000 miles per hour. I'm sorry, very close. So we're moving at 14,000 miles per hour. When we smack, there's nothing left of us. But we have a little CubeSat that we've just let go of this Sunday. It's called LichaCube. It's a little spacecraft that piggybacked with us. So we have delivered 9 months later. I know there's a pregnancy joke there somewhere. But yeah, it's an Italian CubeSat. It actually left, and it's now on its way. It's going to fly by after we impact, 3 minutes after we impact, and take some images of what did we do? Did we do something? So we have been rehearsing this for quite some time. This is from our latest mission rehearsal. We go through these simulations where everybody is on console trying to make sure that we can execute contingency procedures if needed. And so this is from our recent simulation. We've even rehearsed celebrating, which was pretty exciting. But at this point, we really are just waiting. I'll let you watch the trailer because, Oh yeah, we have really cool rollout solar arrays that never been flown in space. Camera, like what took New Horizons pictures. Yeah, if you remember images of Pluto, same camera. And first of a kind next C ion thruster, which accelerates ions. And we deployed LichaCube. Done. Check. Coming to the theater next to you on September 26th. All right, so you too can become a planetary defender. If you go on our website and you take a little quiz, now I believe it's up to 10 questions. There used to be 5 at launch, so you could have gotten your badge then, but you didn't, clearly. So now you have to answer 10 questions about asteroids and what you heard about today, and you actually get a badge that you're a planetary defender. I don't know what it gets you, but there's something. So, of course, we'll be streaming all of this live to NASA TV. Literally, you can go on any website and you'll be able to see us actually hitting an asteroid. So 7:14 p.m. Monday, not next Monday, Monday after that. So the live coverage begins at 6. So please come watch us hit an asteroid. Thank you. It's late by 2 minutes. I hope that's okay.
Fantastic. All right, so we can take questions both from folks here in the live audience as well as folks, if you type it into the chat online, it'll come up here and relay to me. Does anyone have any questions for Elena? Yeah, come on up to the mic.
Hi. I was just wondering, this trajectory is for a binary system, so I was wondering how you guys are planning on changing the trajectory for a system that may not be binary, or what are the thoughts for future different systems?
Oh, that's a really good question. Actually, it's spot on. Because this is just the test, right? So the whole idea here is to be safe, and by just changing the orbit slightly, by 1%, you don't have to worry about it, leaving the system or, impacting anything, and the main asteroid will still go around the sun the same way, and so super safe. In the future, if you did have an asteroid coming towards Earth, it has to be a little different, right? The first thing you would do is you would do a reconnaissance mission. So you would get something up as quick as possible, and you would fly it by of course, you would observe things from the ground, but you would actually want to do a quick flyby of that mission. And in fact, the Planetary Decadal Survey that NASA puts out every 10 years recently just added a planetary defense section to it. And that was #1 thing. Go fly by an object and make sure that you actually would get something out of it, right? Because you can fly by objects, but did you detect anything, right? So the idea is that you would actually do a quick flyby, you would figure out what the asteroid is made out of by just taking some remote observations. And then you send that data back to Earth, so that will inform exactly where you would want to hit it, how you would want to hit it. But the actual aspect of hitting it and seeing how much it moves really does depend on what it's made out of. So this will inform a lot of the models going forward about how you would do this safely.
All right, other questions in the room? Yeah.
Thank you so much. My question is, I was wondering why there is such a range from that like 70 to 55-minute range that you gave for when Dimorphos would come into view. I was wondering if it's just like a lack of constraints on the orbital parameters, or why you have, that range there.
Oh, yeah, so we vary a lot of things, right? We vary the shape of the asteroid, we vary the albedo of the asteroid, the size of the asteroid, then how well is our instrument performing, how well is our spacecraft performing, which way the spacecraft is pointed, how much noise there is, and all the different sensors. All of that combined together, you run these giant Monte Carlo models, and you run hundreds of thousands of cases that vary all sorts of things about the models. And so we have a nominal case where, at 55 minutes, we'll see the asteroid, and everybody will be happy and go home in 15 minutes after that and sleep better. But, there are other cases too that have it brighter, and then we detect it earlier, or had it dimmer when we detect it at 35 minutes. At some points, we actually will try to intervene from the ground because we have that ability, and we're going to try to change the exposure time of our imager, for example, in order to be able to get it brighter enough so that SmartNav can do its thing.
Thank you.
We had one question from online, which you may not want to think about, but what happens if it misses?
We do not have a party. Maybe it's a pity party. No, we do have a plan. And my goodness, I don't even know where to start. We have 21 contingencies, right? Where we figure this mission is autonomous, and part of it is demonstrating the fact that we're doing this autonomously, right? But in case it doesn't work, in case we're having issues, we have contingencies we can execute from the ground, because you have 44 people in the mock either being really bored and just looking at telemetry, or being way too excited, which we don't want. So we have things we're going to execute depending on what we're seeing in the data. But in case we miss, there is a contingency. The contingency number 21 is actually the miss contingency. We will pull up our chairs and I'll say, hey, execute our contingency 21. There will be no celebration in the mock. And then we will continue doing a couple of things. First, we need to make sure why we missed, right? So if it's just our SmartNav almost worked but wasn't smart enough, then we actually we get the spacecraft safe, and then we make sure that we're still in contact, we get all that data down, and then we start conserving propellant. And by conserving propellant means that we are going to try to come back in about 2 years and try to hit. So, and as I think I mentioned earlier, we like to hit all the major holidays. But so this one would be October 31st, 2024, so really on Halloween. We would scare ourselves for sure. So but of course it requires us turning on our NEXI ion thruster, and so there's some risks associated with that, but we don't want to do this. We want to do it the first time. So yeah, we do think about these things a lot, and I think about it a lot at the middle of the night.
Any other questions in the room? Think about it. Yeah, come on up.
So, when it impacts, there'll be a lot of debris generated. Will that not create space debris? Are you not worried about that? Like for future missions that might interfere with something else?
So there are some models that show that most of that debris is going to settle out on the asteroid. So there's that. But also for Hera mission, they're going to come in very slowly, and then they're going to do a slow rendezvous with the asteroid. So the space debris, we're too far away from Earth to worry more about, usually people think of space debris like, oh, maybe a rogue country blew up a satellite in orbit, and now there's more stuff around in low Earth orbit. We are so far away out in the interplanetary space that we don't have to worry about the space debris so much. And most of it is gravitationally captured in that system anyway. Yeah. And here we'll have some good imagers and other things, other CubeSats that will really characterize it. Part of it is actually figuring out just how much debris we'll create. So.
Online, how big is the DART team? How many people are working on it? And I'll add, is it scientists and engineers or primarily engineering?
So we don't call them scientists because this is an operational mission, right? This is a different mission than the usual science mission that you hear from NASA. This is an operational mission. We're here to actually test out a technology. So this is a technology demonstration mission. And planetary defense is not science. It is an actual act of protecting the Earth. So there are investigation team members. You know, what's in the name? They're scientists. So we have both scientists and engineers. At the height of building up the spacecraft, which, by the way, happened in COVID times, which was really fun, let me tell you. While the rest of the nation went home, we had to build a spacecraft, because you can't build a spacecraft not inside the lab. So at the height, we were at about 1,000 people working on it. Right now, we're in about 100 people, plus the investigation team members that are all over the world. Now they're getting more excited, because for a while there wasn't as much to do. But now that we're getting ready for ground-based observations, where it transitions to another phase, we're getting more people there. So yeah, it's great to lead such a cool, diverse team, I have to say.
Any more in the room? Yeah, come on up.
Hi, I was going to ask, if this mission succeeds, what's the next step in planetary defense?
Yeah, so there are a couple of things. So number one is, you know how we looked at those data, like 42% found? Finding these things is the next step, right? So there's going to be a telescope that's going to be going up. It's called the NEO-Surveyor mission, or NEOSM for short, because why wouldn't it be? Right after DART comes NEOSM. So NEOSM is actually going to go up. It's a 0.5 meter infrared telescope, because you can see these things much better in infrared. They actually glow in infrared. Invisible, they have to be lit by the sun in order for you to be able to detect it. So you can only look at a portion at a time. In infrared, you can actually have a much better chance of detecting them. So there's a 0.5 meter telescope that's going to be going up, and it's being built right now. And then after that, we're probably going to do a rapid flyby mission to try to see what can you learn from a rapid flyby. And I just, can I just geek out for a second? So there are many different ways of doing asteroid mitigation, right? So people have talked about kinetic impact is just the most straightforward one, right? You go and hit something and see if it moves. Okay, 1/2 m squared. But there's also many different ways, such as gravity tractor, where you go and you fly in formation with the asteroid, and the gravity of your spacecraft will actually move it enough. There's like, people talk about putting aluminum foil, basically, for the lack of the better words, all over the asteroid, and then the solar pressure, the pressure of the radiation from the sun, will actually move it as well, which, you know, you don't need to move it that much, right? But it builds up over time. There's also different ways of doing it, such as laser ablation, giant laser, you know, ablating the side of it, and it's going to try to move that. So, but all of these things rely on being able to detect it early enough and to make a difference. Of course, in the worst case scenario, there's a nuclear scenario, which, you know, you guys probably way too young for the Armageddon movies, unless the kitsch factor, but, you know, but don't look up approach, where you have a nuclear detonation nearby an asteroid, where the shock wave from the detonation actually moves it. And those would be used for something that is very large. But it does rely for you to be able to quickly put a team together and really get it up there, and you know where it is. So really understanding the trajectory of these things is extremely important. Okay, I'm done. Please, next question.
Still time to send Bruce Willis, though, right?
Oh. You know, there's a moment in that movie where he's standing on the asteroid, and it's literally, he has grass underneath his feet. I'm like, really? Come on, grass? Okay, sorry.
So this does relate to a question online. Someone asks, Dr. Adams, popular culture loves asteroid impacts when it comes to books and movies, and they shape the public's perceptions. Are there any books and movies in the genre that you do like?
Ooh. Well, I mean, who doesn't love Armageddon? I mean, there's Deep Impact, of course, and I don't know. I did watch a portion of Don't Look Up, but I'll be honest, I I'm embarrassed to say it so, but it came out right around the time of DART launch, and I was really busy, and I fell asleep after 4 minutes. And I know I should go back and look at it, but you know what? After September 26th, I'm going to have plenty of time to go back and review all the literature. And exactly.
Do we have any others in the room? Yeah, come on up.
Although my favorite geeky movie is The Core, which is even crazier, right? Giant diamonds. Oh, what? Who comes up with that stuff?
Hi. First, thank you for your speech. It was so good. And I heard that in your speech you mentioned multiple times how this spacecraft is completely autonomous. So I assume that one of the biggest challenge might be, navigation and how to have enough fuel to supply it throughout the whole journey. So I was wondering, what do you think is the biggest challenge, if it's the biggest challenge, if not like the biggest, one of the biggest challenges throughout this whole project?
Oh, okay, so fuel, you brought up fuel. That's a really good question. Because we've been worried about fuel for a long period of time while we were building the spacecraft. So what happened was, I'll give you a little bit of history. So the mission originally was going to be using the Next-G ion thruster as the primarily method of propulsion. And that uses xenon fuel. And then we had these really small hydrogen thrusters that we were going to pulse, and that's a way for us to control attitude. Well, so in developing new technology, that's one of the lessons learned, is definitely it's hard to develop new technology. And you can't rely on it in order to meet your requirements. So our requirements, go hit an asteroid. And when you're building new technology, you don't want to say, we must have this as well as many other new technologies in order to be able to do this. So about halfway through the program, I made the call that we're not going to be using the Next-G propulsion system as our key means of getting to the asteroid, because it wasn't getting there fast enough. Well, it did get there fast enough, but we already made a decision to go to using hydrogen thrusters only. And we only had 50 kilos that we were able to squeeze into the tank. So we were very concerned that we might not actually make it. So we were rationing that propellant gram by gram. Happily, SpaceX actually put us in a really good trajectory. We're going to be hitting this asteroid with about 30 kilos in our tank still. So that's a plus. We bring more mass to make a bigger change. But still, to me, the biggest challenge has definitely been the ability to understand what's going to happen in that system. Because, so as I said, we don't see the asteroid until very late. Our ability to change our course is impacted very late. So early on when you're launching, right? So it's kind of like you're driving a car from LA to DC. You can make course corrections as you go along. Your GPS is like, oh, there's there's construction there, go around it. And that's what we've been doing this whole time. We're going around different construction sites. But by the time we get to the 4 hours out, we're on a clear trajectory, and the spacecraft has to make it's basically we're taking the hands off the wheels, and the spacecraft itself has to make the course corrections. It has to be able to talk to GPS and figure out which way it's going to go. So that's still the biggest concern, that we're going to introduce something to the spacecraft where it's going to see some stars that look a little bit different, right? Or the asteroid is not exactly where it's expected. And what if we miss? So, yeah, not challenging. Oh, and by the way, we have also these really long solar arrays. Long solar arrays, for the first time in our lives, we launched these solar arrays that are basically roll-out blankets. You saw them roll out in the trailer. So they're basically like snap bracelets. You roll them out, and it snaps, and it tightens up. But it's still flexible enough that it introduces a motion to the spacecraft. So you're trying to point this camera that is only a quarter of a degree of the field of view. So you can see from like New York to DC a 1 meter object, right? Crazy. So you're trying to point this thing while these things are flopping about. You're trying to point a high gain antenna on Earth so you can send the video back to Earth. And while maneuvering the spacecraft to try to hit an asteroid that is actually coming out from behind the bigger asteroid at that time. So yeah, that's challenging too. Sorry, get excited.
Great. Hey. So we had a question from online. At what point in the orbit do you hit Dimorphos? Will you be giving it a forward push or a backward push or sideways? And then is there an optimal place if for a real object that we wanted to deflect? Is there an optimal place to hit it, or does it depend on the trajectory?
So all very good questions. So we'll start with the first. We're going to slam into it, face on. It's coming out to us. We're slamming into it. It's going to put it into a smaller orbit. And then there was a question about something else. Sorry.
Real object that might intercept the Earth.
Yeah, so you want to hit it in the middle. You want to hit it in the center of the field of your asteroid as much as possible. You transfer all of that momentum in. If you hit it a little bit on the side, you start creating a little bit of a spin, but that's still not big enough in effect. I mean, the angle of impact matters, but it doesn't matter enough that you will, for example, we will still move it enough that it's noticeable. So we've done all those studies where we slam into it in different orientations, and we still make enough of a difference. So right now, our requirement is 73 seconds. We changed the orbit by about 73 seconds. We're predicting about 10 minutes. If we slam into it at a very oblique angle, it's only about 3-minute change, but still good enough to meet a requirement.
Other questions in the room? Yeah. Yeah, you want to come on up to the mic?
Hi, really great talk. I'm wondering how the SmartNav system was trained, because as you said, the target appears at the very end, and it seems like a very much one-off event.
Yes, it is a one-off event. That's what makes it so hard. That's one of the things, right? So what, we all had crazy ideas of how would we train it, right? Some of them involved with like making a realistic asteroid and then hiding it far away and having our imager try to track it. No, we had a grocery store a few miles away, and we were like, oh, if we put something on top of the grocery store, we can have the camera on, at APL. And yeah, no, that was dumb. But we do a lot of simulations, and it's the varying of all the different mechanisms, and then doing it on flight. We track stars, and we try to fool them that they are actually the asteroids, and we try to switch. So here, what I showed is we switch from tracking Jupiter. When Europa emerges, we fool it to think that that's Dimorphos emerging from behind it. Because over the 4 hours of our terminal, we're actually going to see Dimorphos emerge from behind Didymos. And that's the other thing, right? We don't know exactly the phase of Dimorphos, which means that, I think the previous question was, where are you hitting it? We're hitting it as far away, so when there's Didymos, there's Dimorphos. Dimorphos is going to emerge from behind Didymos. It takes 4 hours to do that. So we're going to be, as we're getting into terminal, in theory, it's behind Dimorphos, and it's behind Didymos, and it's going to emerge if we hit it from here, right? So we train the SmartNav to detect it using Europa just when it starts to emerge. Of course, in real life, it's probably going to be too dim for us to actually watch it emerge. Because of the same issue, right? We don't see it until about an hour out. So at that point, we should be able to, everything should line up perfectly. But we vary these things. We vary the phase, right? We say, yeah, maybe it doesn't emerge in 4 hours. Maybe it emerges at, let's say, 2.5 hours. Can we still hit? The answer is yes. Is it harder? Yes. Are we going to be more nervous? Definitely. So.
Great. We had another question from online. Oh, did we have one in the room? Oh, yeah, okay. We had one from online for an object that might threaten the Earth in sort of this danger zone of 42% range. How far out for a DART-sized spacecraft would you need to intercept it for it to not hit the Earth? Or would you scale up to some larger object?
All right, that's a good question. So there are two answers. So the first one is if you took DART, let's say you took Dimorphos, you stuck it in the same orbit as Didymos right now around the sun, but it comes actually at Earth. You'd want to intercept it, right? So it takes 2 years right now for Didymos to orbit the sun, right? 2 years, 2.11 years. close. So, so you would want to hit it when it is actually at the closest point at Earth. And so that gives you 2 years for it to actually change the orbit enough that it would miss the Earth, right? So that's pretty straightforward. But also, can you hit it with the DART-sized spacecraft at 2 years out? Is it going to miss? No. The answer is 680. We were 616 kilograms at launch. We're going to hit it with about 580 kilograms. The size of Dimorphos is actually 5 billion kilograms, right? That's 160 meter size. So you really are throwing like a baseball at a 747, right? So it's just not making that much of a difference. So what you would need to do in this case is you hit it early enough. If you detected something like 10 years prior to this, and you can get something up there, and you have 10 years for it to actually propagate that through, then something DART size could work. Or you can have it weigh something like 15,000 kilograms, and you hit it at the closest approach, and then 2 years works. So there are different ways of working this, and depending on the size of your launch vehicle that's available, your rocket that's available, you might want to have a different, and how early you detect, you could have a different strategy.
Launch vehicle that can launch 50,000 kilograms to near Earth object?
Well, I hear there's something called Starship coming up. Yeah, so there's definitely, that's a possibility. And it doesn't have to be, it could be something where you hit it with 2 different things. You have 2 launches simultaneously, and you try to hit it with 2 things. There are creative solutions to all of this as well.
You could have 100 DART spacecrafts that you would be in charge of.
No, that sounds miserable. I think we'll stick with 2. You build the same one, launch it in 2 different launch vehicles. If one doesn't work, at least you have the second one that would actually do the job. So in this case, if this is a real threat to Earth, you'd want to think about redundancy. We were cheap. We couldn't think about redundancy.
My question was very much in line with that last one, but basically, just from the other side, is there a minimum time that would be required from detection of an object that would impact to when you could feasibly do it? Or it sounds like it's a lot more complicated than that.
No, that's a really good question. The answer is yes, there is a minimum time. It all depends how long you have time to you need to be able to track the asteroid enough to understand its trajectory, right? So if it's a threat to Earth and 6 months later it's actually going to impact, most likely, as I said, moving to Mars is always an option. But is there, beyond 6 months, is there a real clear cutoff? I don't really think there is. It's just, it really does take time to figure out the exact trajectory of an asteroid. And for that, you need to track it a lot. Doing a quick flyby reconnaissance is a good idea, but you need to be able to actually know where that asteroid is for you to fly by it too, right? So it's not as easy as that.
So we've got about 2 minutes left, and I just wanted to wrap up with one final question. For the Hopkins undergrads here in the room and online, do you have any advice on how they too could blow up a space rock someday?
Study hard. No,
what the sort of applicable fields might be, and pathways to get involved in this field?
Yeah, so I'll be honest, my career took me all over the place, right? My minor is in history, so there you go. But yeah, so you can be a scientist engineer, you can be a communicator, you can be a teacher, you can do many different things and still get involved in planetary defense, because at the end of the day, it is kind of a global concern. We have people from lawyers who are involved in it, because guess what? You can't do anything without lawyers. But but I'm serious, because you quickly get into questions of, if an asteroid was coming in and was trying to impact an area, how do you deal? Whose principality is that, right? Are you talking about North Carolina? Or, there's just a lot of legal issues with that as well. But also, you really could be anyone to work on planetary defense topics. I mean, we have a lot of really brave people in the military who are working on planetary defense. You have to give a shout out to Space Force, because they're new. and they have cool uniforms. But you know, they're also very much interested in planetary defense. So there's something for everyone.
All right, let's thank Dr. Adams one more
And
time.
for geologists too.
Thank you so much for coming. And we'll be live streaming this the Monday after next week on campus, right? On campus. Kaiser Quad.
Starting at 6, party countdown starting at 7,
7:14, 24 seconds.
All right.
Just
Be there the week after next. All right.
Yeah.
Thanks again.
so, hope you guys enjoyed it. Thanks.